Let's talk about what are known as the reciprocal and quotient identities. So first, the reciprocal identities say that cosecant of x is equal to 1 over sine of x, secant of x is equal to 1 over cosine of x, and cotangent of x is equal to 1 over tangent x. Of course, you could rearrange all of these and find things like sine of x is equal to 1 over cosecant of x, and similarly for all the others. But if you can remember these three, you can remember all of their rearrangements. So these are the reciprocal identities, and then the quotient identities are down here. And they just say that tangent of x is equal to sine of x over cos of x, and cotangent of x is equal to cosine of x over sine of x. Of course, if you can remember that cotangent of x is 1 over tangent of x, then cotangent of x should be cosine over sine by this identity. So these are all interrelated. If you can remember one, you can often remember the others. These are the quotient identities. And just as a quick example, these can all be verified using what we know about the definition of the trig functions of an angle given a point that it goes through. So, for example, if we know that an angle, this is the point xy, and r is the radius, then things like, we know that sine of x is defined to be y over r, and cos of x was x over r. And so if we think about and similarly tan of x, these should all be thetas. The angle is theta. So sine of theta y over r, and cos of theta is x over r. And then tan of theta was y over x. So if you think about how these all relate, and think about our quotient identity, well, sine of theta over cos of theta is y over r over x over r. And when you simplify the r's, you just get y over x. And that agrees with our definition for tan of theta. So that's how you can see that there's nothing really new here. This is just a different way of representing what we already know about relationships between the trigonometric functions. But let's look at a few examples. So, if sine of x is 2/3, what is cosecant of x? Well, these are all relatively straightforward. We know that cosecant of x is 1 over sine of x. So this is just 1 over 2/3. Dividing by a fraction is multiplying by a reciprocal, so we get 3/2. Now we're told that cosine of x is 1/4, and we want to know what secant of x is. Well, remember, secant is just 1 over cosine. And so we get 1 over 1/4, and that's just 4. So again, these are straightforward, but it allows us to quickly find one function value given the other, and that's why this is useful. Now as another example, if secant of x is equal to 3, what is cosine of x? Well, remember that these reciprocal identities go both ways, right? If secant is 1 over cosine, then cosine is 1 over secant. So cosine of x is 1 over secant of x. So it's 1 over 3. Now, if cotangent of theta is 4/3, then what is tangent of theta? Well, again, cotangent was 1 over tangent, so tangent is 1 over cotangent. So tan of theta is 1 over cotangent of theta, which is 1 over 4/3, which is 3/4. Now we're told if sine of x is 5/13 and cosine of x is minus 12/13, then what is tangent of x? Well, this is using our quotient identity. The quotient of interest here is that tangent of x is sine over cosine. And since we're told that sine and cosine are, we can just plug them right in. 5/13 in the numerator and minus 12/13 in the denominator, and the 13's cancel. We can multiply top and bottom by 13, leaving us with minus 5/12. So that's what tangent of x is. So now we're told what sine of theta and cosine of theta are, and we want to know what cotangent of theta is. Well, now again we use a quotient identity. In this case, the quotient that we're interested in is that cotangent is cosine over sine. And we're told that cosine of theta is square root of 7 over 4. And that sine of theta is minus 3/4. And again, we can multiply top and bottom by 4. They cancel, leaving us with the square root of 7 over minus 3. So minus the square root of 7 over 3 is cotangent of theta. Okay. So one other use that we have for these quotient and reciprocal identities is to simplify certain trigonometric expressions. So, as an example, let us simplify sine of x times tangent of x times cosecant of x times cosine of x. And some of these, they seem like they're messy and you wouldn't know what to do. So a good strategy in this situation is just to write everything in terms of sine and cosine. That's what the reciprocal and quotient identities allow us to do. So sine of x stays as is. It's already written as sine of x. And tangent of x by the quotient identity can be rewritten as sine of x over cosine of x. And then cosecant of x by the reciprocal identity can be written as 1 over sine of x. And cosine of x is already written in terms of cosine of x. And now once you've written it out like this, we can quickly see the cancellations that need to be made. So in this case, we have a sine of x in the denominator that can cancel with the sine x in the numerator over here. We have a cosine of x in the denominator over here that can cancel with this cosine x on top. And we're left with just sine of x. So this simplifies to sine of x. Now we're asked to simplify secant of x times cotangent of x times sine squared of x. So again, let's rewrite everything in terms of sine and cosine. So secant of x is 1 over cosine of x by the reciprocal identity. Cotangent of x is equal to cosine of x over sine of x by the quotient identity. And sine squared x is already in terms of sine x. Okay, now let's see what cancellation happens. We have a cosine of x in the denominator and in the numerator. That'll cancel. And then we have one factor of sine x. So this leaves us with a single factor of sine x. And now everything is canceled but for one factor of sine of x. So that's what's left.